Today's notes are over solving exponential equations. So let's look at some other types of equations where we've solved for the value of the variable. In this first example, that's a linear equation, we're going to solve for the value of the variable just using basic inverse operations. So I'm looking for the value of x. I'm going to add 5 to both sides, and I get 3x equals 12. And then I'm going to use the inverse operation of multiplication, which is division. I'm going to divide both sides by 3, and I get x equals 4. So there's your very basic example, the first types of equations that you ever learned how to solve. And then the next might have been an absolute value equation. So I've got a little reminder here. Remember to set up two cases because we're going to have two answers, most likely, in this absolute value equation. So the first thing I want to do in an absolute value equation is get the absolute value portion all by itself on one side of the equal sign in this particular example. So I'm going to divide both sides by 2, and I get the absolute value of x plus 5 equals to 8. And now I'm going to set up my two cases. Okay, the first case is going to be x plus 5 equals 8. And the second case is going to be x plus 5 equals negative 8. And I'm going to have an or in the middle there, right? Okay, so when I solve for the value of the variable in the first case, I subtract both sides by 5, and I get x equals 3. There's one answer choice. Or x could also be subtract by 5, and I get negative 13. So those are my answers in the absolute value equation. And then the last one that we're going to do for our little review portion of these notes are this quadratic equation. And my little reminder says, remember to factor first. So this is what I call a slide and divide trinomial. So I slide that first one and then the last, and I get, which you might factor this differently. I've taught it like so many different ways, but this is my favorite way. I need two numbers that multiply to negative 6, add to 1. Those are positive 3 and negative 2. So x plus 3 times x minus 2, and then what I multiplied into my last term, which was 2, I need to divide out, simplify, and I get 2x plus 3 times x minus 1 equals 0. So when we solve this, we need to factor, and I factored this slide and divide trinomial, and then I'm going to set each factor equal to 0 using our zero product property to solve for the value of the variable. So in the first one, I'm going to do 2x plus 3 equals 0, and x minus 1 equals 0. And then I'm going to solve for x. And this one actually looks like that linear equation up top. Subtract 3, divide by 2, so I get x equals negative 3 over 2. And when I add 1 to both sides, x equals 1. So that's a review of some equations that we've learned how to solve thus far. And we're moving on to exponential equations. So this is today. We're going to be doing exponential equations. What is an exponential equation? So in an exponential equation, the variables are found in the exponents. So if you see that like x variable as an exponent, that's an exponential equation. And in this first type of exponential equation, we're going to be looking at equations that have the same bases. Okay, so if the bases are the same, then the exponents must be equal. So if you think about it, if b to the power of x equals b to the power of y, then x must equal y. And I've got this little caveat right here. B can't be 0, b can't be 1. Okay? So if you think about it, like if 3 to the power of 2 equals 3 to the power of x, well, then x must equal 2, right? So that's how we get this. I'm going to erase this little portion right here. And let's get started on our examples. In example number 1, taking a little bit of time to erase. In example number 1, I've got 3 to the power of x equals 3 to the power of 2x plus 5. So I've got the same base here. What I can do is just eliminate those bases and set my exponents equal to each other. And then I'm just going to solve for the value of the variable. I got to move my variables to one side, so I'm going to subtract 2x from both sides, and I get negative 1x, or negative x, equals 5. I don't want what negative x equals, so I'm going to divide by negative 1, and I get x equals negative 5. And you can always go back and check your work, right? 3 to the power of negative 5 equals 3 to the power of, well, 2 times negative 5 is negative 10. Negative 10 plus 5 is negative 5. So that works, right? 3 to the power of negative 5 equals 3 to the power of negative 5. Let's move on to number 2. So at first glance, I notice that these expressions do not have the same base. But what I always want you to do first is try to rewrite your expressions so that you create expressions with the same base. So I can actually rewrite 8 to be 2 cubed. So I can rewrite 8 so that I have a base of 2, which is the same base that's on the other side of my equal sign. So now what I've done, 2 to the power of x equals, I can rewrite 8 as 2 to the power of 3, and then I'm going to raise that to x minus 2. And now my expression almost looks like what it looks like on number 1. But what I need to do is simplify the right side of the expression. So 2 to the power of x equals, how can I get rid of those parentheses? I can use my power rule. So I'm actually going to distribute this 3 into each term, right? So that's like 3 times x minus 2. So I'm going to get 2 to the power of 3x minus 6. And now this looks like our problem number 1. So I've got the same base. I'm going to set those exponents equal to each other. And now I'm just going to solve for x. So I subtract 3x from both sides. Negative 2x equals negative 6. Divide both sides by negative 2, and I get x equals 3. And problem number 3 is the most difficult in this section of the notes because at first glance I cannot change the number 27 to have a base of 9. However, I can actually change both 9 and 27 to have a base of 3 because 3 squared is 9 and 3 cubed is 27. So I could actually change both sides of my equal sign. So the expression on both sides. So if I were to do that, on the left side of my equal sign, that's going to become 3 squared raised to the power of x equals, remember, and it's a good strategy to just like whatever you're replacing, put whatever you're replacing in parentheses and only replace that. And then everything else stays where it is, right? So like I'm going to change 27 to 3 cubed. So I'm going to put 3 cubed in parentheses and then everything else stays right there. Right, so now I've got to do what I did on this first step on the example number 2. So I need to simplify the left side. That's going to be 3 to the power of 2x. And when I simplify the right side, I distribute that 3 into each term, okay, and that exponent outside of the parentheses. So that's going to be 3 to the power of 6x plus 12. And now my equation looks like it did on example number 1. So this is always going to be your first strategy. Can you create expressions with the same base? And if you can, do that and set your exponents equal to each other. When I subtract, or when I move my variables to one side, I'm going to subtract that 6x. I like to move the variables to the left. So I get negative 4x equals 12. Divide both sides by negative 4, and I get x equals negative 3. And you can always go back and check your work. For the sake of time, I'm just going to move on. In the next portion of the notes, you are going to need your calculator. So whether or not you have a TI 84, 83, Inspire, whatever you have, grab it. If you use Desmos online, that's another good calculator that I strongly recommend. But you are absolutely going to need a calculator for this portion. So in this portion, you will have different bases. If the bases are different, what we're going to be doing is taking the log or the logarithm of both sides. And then we're going to apply our properties of exponents. So I'm going to ask you to remember those properties that we've gone over in previous lessons to simplify our expressions and solve for x. And we will be using a calculator to find our answer. And our answers will be approximate, okay? So we will be rounding. So let's look at example number 4. It says 6 to the power of x plus 1 equals 100. And when I look at this example, I know that I cannot create expressions with the same base. And I know I have an exponent, or I have a variable in my exponent, so I'm going to take the log of both sides. I'm going to take the log of 6 to the power of x plus 1. What I do to one side, I have to do to the other, so that's log of 100. And then I'm going to apply my properties of logarithms. So what can I do with this exponent up here? I can move it out in front. So that's the same as x plus 1 times the log of 6 equals the log of 100. And remember, our goal is still to get the variable all by itself on one side of the equal sign. So this is x plus 1 times the log of 6. So what I'm going to do is divide both sides by the log of 6, and I get x plus 1 equals the log of 100 divided by the log of 6. And this is where you're going to use your calculator. So grab your calculator right now and type in the log of 100. So log of 100, then close parentheses, divided by the log of 6, close parentheses, and press enter. And you should get approximately 2.5701. So I'm actually going to write that down. So x plus 1, and we're going to approximate this to 0.5701 ... right? It continues. And now what you're going to do, don't erase your screen. I'm going to subtract 1 from both sides, right? So you could just do subtract 1 and it'll say answer minus 1. So this section of your notes, whenever you're using a calculator, do not round until the very, very, very end, okay? So when you subtract 1, now you've got x is approximately 1.57, and then I take it out 3 decimal places because that's what you typically do on an AP Calculus exam. So 1.570 if you even wanted to write. So there's your answer. X is approximately 1.57. Let's move on to number 5. So number 5 is another example. I cannot create an expression with the same base, so I'm going to take the log of both sides. I'm going to do exactly what we just did. So I'm going to take the log of 3 to the power of 2x equals what I do to one side, I have to do to the other. Log of 20. Apply my properties of logarithms. I can take that exponent and make it where it's 2x times the log of 3. And I want to show you that I don't need those parentheses whenever I do this. I just did it on the last one. And again, our goal is to get the variable all by itself. So that's 2x times the log of 3. I'm going to divide by the log of 3 to get rid of it. What I do to one side, I have to do to the other. And now you're going to grab your calculator. And I'm actually going to be making a tutorial video over how to plug in logarithms and stuff like that on your calculator. So you can look for that on my channel. And whenever I make it, I'll put a little card in the upper right corner right here so you can click on that and it'll take you to that video. So now you're going to plug in log of 20, close parentheses, divided by log of 3, close parentheses. And what do you get? You get approximately 2.7268. It keeps going, going, going. And now I'm going to divide by 2. And you're not going to change anything. Just do divided by, plug in divided by 2, and it should say answer, like ANS, answer divided by 2. If you're using Desmos, what you really need to do is put your entire expression up here in parentheses and then divide by 2. Okay, so log of 20 divided by log of 3, then divide by 2. And you get x is approximately 1.363. And that's your answer for number 5. Let's move on to number 6. in problem number 6. And hopefully you start getting the hang of it. Sorry, moving right along. It's taken forever. Okay, I can't create expressions with the same base, so I'm going to take the log of both sides. That becomes log of 4 to the power of negative x. What I do to one side, I have to do to the other. Log of 25. Again, I'm going to apply those properties of logarithms. That's going to be negative x times the log of 4 equals the log of 25. I'm getting x all by itself, so what do I do at this point? Divide both sides by the log of 4, so I get negative x equals the log of 25 divided by the log of 4. And go ahead and pause this video and plug that into your calculator. And you should get 2.3219. But I don't want what negative x equals. I want what positive x equals. So x is approximately negative 2.322, right? I'm rounding to that third decimal place, that thousandths place. So that's problem number 6. Let's move on to problem number 7. And problem number 7 says 18 to the power of 2x equals 9. Now, a lot of students, when they see a problem like this, they go, oh, I can create expressions with the same base, right? 18 and 9. 18 divided by, 9 is a factor of 18. Well, no, you can't create expressions with the same base, though, okay? 3 squared is 9. 3 cubed is 27, right? 9 squared is 81, not 18. So you can't do that in this one. So what we have to do is take the log of both sides. So again, log of 18 to the power of 2x equals the log of 9. Apply those properties of logarithms. I can move that 2x out in front. 2x times the log of 18 equals the log of 9. And what do you think I would do at this point? That's 2x times the log of 18. So I'm going to divide both sides by the log of 18. So I get the log of 9 divided by log of 18, and you're just going to plug that into your calculator. And remember, we're not approximating yet. We are going to round when we write it down on our paper or this PDF, but we're not going to round till the very, very, very end. So log of 9 divided by log of 18 is 0.7601 ... and then divide by 2, right? Because we're going to divide both sides by 2 to get x all by itself. Oh, that should not be x equals because we are going to round. It's x is approximately 0.7601 ... divided by 2 is approximately 0.38 or 380. Let's move on to problem number 8. Number 8, 7 to the power of x divided by 4 minus 1 equals 18. I can't create expressions with the same base, so I'm going to take the log of both sides. Oops, let's see. Okay, so that's going to be the log of 7 to the power of x divided by 4 minus 1 equals the log of 18. And now I'm going to rewrite that expression on the left. I'm going to move whatever is in the exponent up here, right, to the front. So that's going to be x divided by 4 minus 1 times the log of 7. Let's see, I'm going to signify that equals the log of 18. And what do I do now? I get the variable portion all by itself. Well, I can only get this expression, x divided by 4 minus 1 equals, I'm going to do the log of 18 divided by the log of 7. Now, the biggest thing here is we're not going to approximate or round until the very, very end. Okay, so the log of 18 divided by the log of 7, if you plug it into your calculator, what do you get? You get like 1.48535 ... right? It keeps going. Okay, so now we're going to take that and we're going to get this variable all by itself. So I got to undo this side on the left. So I'm going to add 1 to both sides. So plus 1, I get x divided by 4 equals 2.48535. dot, 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 right? And then now, to undo that divided by 4, I'm going to multiply both sides by 4. So when we multiply both sides by 4, you get x is approximately 9.941. And that's your answer. Okay, let's move on to problem number 9. This is the last problem of this set of notes. So I get 2 to the power of x minus 2 equals 10. I can't create expressions with the same base, so I'm going to take the log of both sides. So log of 2 to the power of x minus 2 equals the log of 10. And what can I do with that exponent portion? I can move it out in front. So x minus 2 times the log of 2 equals the log of 10. To get that variable portion all by itself, I need to divide both sides by the log of 2. So the log of 10 divided by the log of 2. Go ahead and pause the video and plug that into your calculator. When you plug in log of 10 divided by log of 2, you should get approximately 3.3219. And then when you add 2 to both sides, now you can round. X is approximately 5.322. And that concludes your notes over solving exponential equations. We've got equations that have the same base, which is what you always want to look for first, and then we've got equations with different bases. So I hope these notes were helpful.